faithfully conveying value, interpreting global masterpieces. Hello, this is Ixama. Today's book for you is 123 Infinity. Using mathematics as a thread, this book introduces major scientific advances since the 20th century. From mathematical patterns to the infinity of our universe, it carries a subtitle, Facts and Speculations in Science. This book was written in 1946, over 70 years ago. When first published in China in 1978, Professor Liu Bin from Tsinghua University was just a freshman. He read it on his calculus professor's recommendation, amazed how a science book could be as gripping as a detective novel finished in one night. Even after decades, Professor Liu still considers this the best science popularization book he's ever read. So, what makes this book so captivating? Unlike typical theme-based science books, it weaves mathematics with physics, chemistry, astronomy, and biology, connecting concepts seamlessly using high school level math to explain relativity. Sugar dissolving in coffee becomes a probability problem. Two telescopes on Earth can measure the sun's distance. It offers a unique lens to observe our world. Author George Gamow was a top Russian American scientist who laid foundations for the Big Bang Theory. His pioneering work spanned nuclear physics, astrophysics, cosmology, even molecular biology. Unlike stereotypically serious scientists, he loved jokes, a prankster described by peers as an eternal child. Today, he'd be considered the meme king of science. This 250,000-word masterpiece, let's explore it through four mathematical tools. First, imaginary numbers guiding us into 4D space. Second, triangle angles revealing spatial curvature. Third, probability theory explaining microscopic motion. Fourth, parallax displacement. With this, we, ordinary folks, can adopt a divine perspective, measuring the universe from a water droplet to the cosmos, transcending from 2D paper figures to 4D space. Let's experience mathematics magic through this mind-bending journey. All right, let's start with mathematics guiding us into four-dimensional space. Let's begin with some groundwork. Remember your multiplication tables. 2 times 2 equals 4, 3 times 3 equals 9, 4 times 4 equals 16. These are square operations. Reverse it. Square root of 4 equals 2, square root of 9 equals 3, square root of 16 equals 4. Simple enough. But have you considered negative numbers, like -4, -9, -16? What about their square roots? Do square roots of negatives even mean anything? In high school math, negatives have no square roots because they're not perfect squares. Yet, these impossible roots keep appearing, like finding two numbers that add to 10 and multiply to 40. The solution shouldn't exist, but paradoxically, using square root minus 15 makes it work. 5 plus square root minus 15 and 5 minus square root minus 15. Mathematicians are stubborn folks. If meaningless things persist, we'll assign meaning to the meaningless. Thus, square root minus 1 was named imaginary number with a capital I, where I squared equals minus 1. Square root minus 4 equals 2i. Square root minus 25 equals 5i minus, like real numbers' mirror world counterpart, seemingly useless beyond calculation, until amateur mathematicians place them on coordinate axes. Visualize a horizontal axis representing all real numbers. Left of 0, negatives, right, positives, no room for imaginaries. Now add vertical axis at 0. This represents imaginary numbers. It points upward, I, 2i, 3i. Now all numbers find their place. 4i sits vertically for 3 plus 4i. Find 3 on horizontal, 4i vertical. Their intersection completes it. You might say this is still useless, right? But actually it's super useful. With this imaginary axis I, diffusion of real and imaginary dimensions ignited a physics revolution, helping establish 4D spacetime models. The fourth dimension often seems mysterious. Can 3D beings truly visualize 4D? It's simpler than you think. A word we use daily represents the fourth physical dimension: time. Time and space together describe events around us. News broadcasts always state both where and when something happened. Thus, all physical objects are 4D, three spatial dimensions plus time. Now comes the challenge. Unifying these dimensions in one model, different measurement units, meters for space versus hours for time. How to reconcile? We need a mediator, speed. There's one universal constant, light speed. Multiplying time by light speed converts it to distance, making time measurable as spatial extent. Like astronomers saying a star is 5 light years away, similar to saying a train trip takes 5 hours. Now, plat coordinates, horizontal for space, vertical for time, defining 4D space-time positions. That space and time remain fundamentally different. Unit conversion isn't enough. This is where imaginary numbers become crucial. Mapping space-time coordinates to real or imaginary axes, time as imaginary, space as real, preserving their distinct nature. To calculate 4D distance between events, square root of spatial distance squared plus temporal distance squared. If the spatial distance between two events is smaller than their time interval, like you reading in the living room at 8 a.m. and your mom cooking in the kitchen at noon, calculating their 4D distance gives a negative value under the square root. We say these events have an imaginary four-dimensional distance. Conversely, if spatial distance exceeds time interval, say you're reading at 8 a.m. and a meteor hits Mars 10 minutes later, the calculation yields positive value, indicating real four-dimensional distance. This real imaginary axis has greater implications. For high-speed objects, these axes rotate, altering event projections. Vertical projections lengthen, horizontal ones shorten. Simplified, time slows and lengths contract for fast-moving objects. Hearing this, do you feel sudden enlightenment? This is exactly special relativity. Who knew meaningless imaginary numbers hid such profound physical significance? General relativity describes curved time. Special relativity, curved space. Next, mathematics and space curvature. We know curves in 2D, but imagine curved 3D space? Einstein said space bends, but how do we inside space detect it? Simple answer, use triangle angle sums. Imagine a 2D paper being detecting surface curvature. Method, draw a triangle. Flat triangles sum to 180 degrees, but not on spheres. Picture Earth's longitude-latitude triangle with two right angles sum exceeds 180 degrees. Clearly exceeding 280 degrees indicates positive curvature. If the sum is less than 180 degrees, it's saddle-shaped, negative curvature. We 3D beings can use similar method. Create triangles with taut strings and check angle sums. Einstein's general relativity states massive objects warp space, greater mass, greater curvature. When Einstein proposed this in 1915, people found it incomprehensible. You might say, just measure triangle angles. How hard could that be? Seems simple enough, right? Let's test it. Surround a mountain with stakes and measure angles. That even using Mount Everest, the angles would still sum to 180 degrees. Mountains lack sufficient mass to create measurable space-time curvature. Einstein proposed using the sun. Create triangle between Earth and two stars with sun inside. The sun's mass should warp space-time, making angles deviate from 180 degrees. Instead of physical ropes, use light paths. Photons follow space-time's shortest routes. Practically, we only need measure angle between starlight paths with or without sun's influence. This angle should change when sun enters or exits the measurement triangle. Crucially, this experiment requires total solar eclipse conditions. Normally, sun's glare obscures nearby stars. Finally, in 1919, during West African eclipse, British team confirmed starlight deflection. Observed light bending proved solar mass works spacetime. Einstein further established the crucial theory that gravity is an effective spacetime curvature. This abandons the concept of gravity as a force, instead viewing it as spatial geometry. When the sun's mass curves surrounding space, Planets glide along this curvature rather than being pulled by solar force. It's like driving on curved highways. We naturally follow bent paths. From these examples, we see Einstein's physics achievements are fundamentally mathematical. Both special and general relativity employ mathematics to analyze motion phenomena.